Hello, hello, hello. Welcome back to Shiksha DaCosta. Today we are going to be talking about stretching and reflecting quadratic relations. And this is part of Unit A1, where we're going to connect the graphs and equations of these quadratic relations. So today we are learning how changing the variables h and k will affect the graph of the quadratic relation given to you by this equation. You're successful at these skills when you can determine, by an investigation using technology, what are the roles of h and k in quadratic relations of this form. And when you can describe these roles in terms of how they will transform the graph of y equals x squared. To start off, I'd like you to really take a second and think about what is happening in these clips right here. What is happening to this piece of dough as these hands are moving apart? What is happening to this red ball of clay as it's sort of being pushed down towards the ground? There are special words that we use to describe these sorts of transformations that we will learn today. This one, it looks like the dough is being stretched. So it's being pulled apart from the edges, and that's making it longer and longer. And similarly, we would say that this red ball of clay, when it's being pushed down and being made into a flat ball, is being compressed. There is compression happening here. So it looks like somebody is pushing it from the top, and there's a hard surface at the bottom. So instead of to try to maintain the same size, the same volume, it has to spread out and get wider. This is something that we will see happen to a few quadratic relations as we go through this lesson. So what you can do right now is graph these three functions on a graphing technology like Desmos. And you can see that's what I've got here. I've got y equals x squared graphed. And what I'm going to do is I'm going to change the variable a. So I've got y equals ax squared here as well, but you don't see it because it is just behind the graph of y equals x squared. And I'm going to change the variable a. I'm going to change 2, and then I'm going to increase it further to 5. Right now, even though you don't see anything there, there is secretly a number 1, right? Anything, if you don't see a coefficient, there's always a secret coefficient of 1. Let me just write that down here. When we increase that value of a to 2, the graph, and you know what, this is a good time for you to pause the video and look at these two, and then see if you can describe what is happening to the graph of y equals x squared as the a value increases from 1 to 2 and from 2 to 5. Okay, let's take that up. So here we can see the graph of y equals 2x squared. So the value of a here is 2. And this is the red graph here. The graph y equals x squared is still here in orange, but 2x squared is here in red. And when we continue that to graph 5x squared, it looks like this. Notice that these 2 points, these 2 red dots here, they have the same x value as these 2 orange dots. And similarly over here, these 2 red dots, they must be the same dots as this because they have the same x value here. So they did not move left or right. Notice that it's still 1 unit away from the y-axis. Over here, the dots are still 1 unit away from the y-axis. But they are much higher up. So it's almost like somebody grabbed these dots from here and pulled them upwards. Pulled them upwards. But they kept one finger kind of pressing down this dot here because this dot did not go upwards. You don't see the red dot on the red quadratic because it's behind the orange one, but there is one here. And so what can we say? How can we describe what happens to the orange quadratic, the quadratic y equals ax squared, as a increases from 1 to 5? we would say that it is the parabola looks like it's getting sort of taller or thinner. What's actually happening is it is stretching vertically. It's like somebody's grabbing it from the top and the bottom and pulling it up and down. Continuing our investigation, let's now look at what happens when we take that value of a, and again, it's starting at 1, and let's see what happens as we make it smaller. Okay, so this is 1 over 4, and this is 3 over 4. Okay, so we've got this quadratic. Again, in red is ax squared. Here we see it when the value of a is 0.25, or 1 over 4. You can see the red dots now are getting closer to the x-axis instead of higher, but they are the same distance from the y-axis. So this red dot used to be this orange dot, and they are both 2 spaces away from the y-axis. So the dots aren't moving left or right. They are just moving downwards. And they're not all moving downwards the same amount. Look, this coordinate, it went down 3 units, but this one only went down not even a whole unit. And I don't even know where this one came from. It must have been all the way up here. Taking a look at when a is 3 over 4, we see something similar, but not as much, right? So when it was 1 over 4, it was really close to the ground. But when it was 3 over 4, the dots didn't move down by too much. And that makes sense because 0.75 is not as small as 0.25, but both of them are smaller than 1. So how could we describe the transformation happening here? How did the orange parabola turn into the red parabola? It sort of looks like somebody really pushed downwards like this. Really pushed down from the top as well as up from the bottom here. And that's what is making the quadratic look like it's sort of stubbier. It looks like it's wider, but it's really just shorter. And the same thing happened here. So what's actually happening is the parabola looks like it's getting shorter and thicker, but it's actually just compressing vertically. So it's only shorter. It doesn't actually get wider than this. Notice the dots here are still the same distance from the y-axis. That's how we know that is true. That's kind of extraneous though. Really the only important thing for us to remember is that this is compressing vertically. So over here, a was a small number, it has decreased from 1 to 0.75, and that way it got a little bit shorter, to 0.25, and that way it got a lot shorter. So it is compressing vertically. Now let's check out what happens if we were to try to make a negative. So we know what the graph of y equals 3 over 4x squared looks like because we just saw it. But what about negative 3 over 4? When we do that, whoa, weird. It looks like the graph has sort of flipped. All of the points have still not moved left or right, but this point has gone to the other side. Notice this is 4 units away, but this is only 3. So not only has it flipped, but it must have gotten a little bit shorter. And we knew that it was going to get shorter because of the graph that we looked at on the previous slide. Right? When it was just 3 over 4, that made it shorter. It looks like what the negative did is flip it over. Let's see if that remains true here. So remember, when a was a big number, the graph looked narrower, thinner, taller. It was stretched vertically. And in this case, this negative seems to have flipped it upside down. Let's see if that will still happen. Yep, it did get thinner, narrower, and it did flip. And so that's why we say that this has this graph right here was compressed and reflected across the x-axis because it got shorter. That's compressed, vertically shorter, so that it was vertically compressed. And then it was reflected across the x-axis, as if the x-axis was like a mirror. Whereas for this graph, we can see that it was stretched vertically. So it got narrower, thinner, taller. So it was stretched vertically, and then it was reflected again across the x-axis. So that concludes our little investigation here. When compared with the graph of y equals x squared, the graph of y equals ax squared is a parabola that has been stretched or compressed vertically, and this is how we use the verbiage here, stretched or compressed vertically by a factor of a. Factor because factor means you're multiplying, and of course this is a times x squared. So on a number line, so I'm just going to put the value of a on the number line and let you know what it does depending on where it's placed. When a is greater than 1, we saw that the parabola, so when a was 1 or so a number that is bigger than 1, not 1, any number bigger than 1, when a was greater than 1, the parabola was stretched vertically. When a was less than -1, we saw that not only was it stretched vertically, but it was also reflected across the x-axis. So there was a vertical stretch and a reflection. Whereas when it was positive greater than 1, there was only a vertical stretch. When a was between 0 and 1, there was a compression vertically. So the parabola got shorter. And when a was between 0 and -1, there was still a compression, but because this is negative, there was also a reflection across the x-axis. So these are the 4 different ways that the variable a can affect the shape of a quadratic. When it's, picture it like you are multiplying, you're taking a person's height and let's say they are just exactly 1 unit tall or 1 meter tall, and you are multiplying their height by a certain number. If you multiply it by a big number, a number that's bigger than 1, this person's height will be taller. If you multiply it by a number that is less than 1, this person's height will be smaller, so they'll be shorter. If you multiply their height by a negative number, by a small negative number, then they're not only going to be shorter, but their height is going to be upside down, right? How do you say negative height? That means you're sort of going into the ground. And similarly, if you use a big negative number, not only are you making them shorter, not only are you making their height negative and flipping them upside down, but you are also stretching them. So they're making them taller. If it's less than -1, you're making them tall and negative. So one way to think about a parabola is to really, and how the variable a affects it, is to think about multiplying your own height by that variable's value. If you're multiplying it by a big number, you get taller, a small number, you get shorter, and a negative number, then you get flipped upside down. Let's look at a few examples here. Let's try to sketch the graph of the equation y equals 3x squared just by transforming the graph of y equals x squared. So these are the coordinates of the graph of y equals x squared. Let's see where the coordinates of y equals 3x squared will be. So we know that this will be a vertical because the a value is greater than 1. We're multiplying it by 3, so there will be a vertical stretch. And another way to think about that is all the y values here, because the y values are equal to x squared. So we're taking those y values, x squared, and multiplying it by 3. So if we want to find the new coordinates locations, we have to multiply all of these by 3. Right? So in this example, a is 3. So the y values of y equals x squared have been stretched by a factor of 3. That's the verbiage we use, by a factor of. By a factor of. So times 3 gets us 27, 4 times 3 is 12, 1 times 3 is 3, 0 times 3 is still 0, 1 times 3 is 3, 4 times 3 is 12, and 9 times 3 is 27. So now I have all my x and my y values. Let's see what the graph of these two parabolas looks like. And there we go. Let's see if my graph was actually, if my coordinates were good. So y equals x squared is here in orange, -3 and 9. So let's see, -3, yep, 9, that looks good. Negative 2 and 4, negative 2, 4. Yep, that looks good. Notice these are going up by 2's. And now let's check the graph of y equals 3x squared, because I'm pretty confident in this one. Negative 3 and 27. 1, 2, 3. 27. Yeah, that looks like about 27. Negative 2 and 12. 1, 2. And yep, that's 12. Negative 1 and 3. Negative 1 and 3. And 0, 0. And notice that on the other side of the parabola, there are the exact same points. 3, 12, and 27. That's because a parabola is symmetrical. It's almost like this line in the middle is like a mirror. And there we go. I have sketched the equation of this graph by transforming this graph. So I've just taken the coordinates here and I've multiplied their y values by 3. And so now they are much further from the x-axis. And if you want to see a little bit more graphical representation of that, notice that the y value here is 9, and the y value for between these 2 points is 27. Okay, and this is 3 times 9. So this distance got multiplied by 3, and I'll show you that just by drawing 9 3 times. 1, 2, 3. That's exactly 9 times 3 gets us 27. And notice that the point itself did not change where it moved from the x and y axis. Sorry, from the distance from the y-axis. So this point was 1, 2, 3 units away here, and it's 3 units away here. And the x values here confirm that. In another example, we have a single point on this graph, y equals x squared. We want to find its image, A prime. So basically, where is its new location if the quadratic was transformed into this, and then its new location if the quadratic was transformed into this. So we need to find its 2 new locations for this point, A prime and A double prime for point A. So in this example, the first example, A is equal to 11. Not the point A, but the variable A was, because this is ax squared, it's equal to 11. And that means that the y values of our original quadratic have been stretched by a factor of 11. So if we take this point, 12 and 144, and we take the y value, 144, and we multiply it by 11, we will get the location of its new location, the location of A prime. And we could just plot that on a graph. In the second example, the value of the variable A is negative 0.25. And so the y values of the original quadratic have been compressed by a factor of negative 0.25. So here is our point, and we are multiplying it, the y value only, by negative 0.25. And its new location, therefore, will be 12 and negative 36. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.